One of our worksheets that we had for homework last night was worksheet number 14. We need to go over number 2 for that one. So let's take a look at that now. Because Michelson used an 8-sided mirror. It's the standard mirror, right? 8-sided rotating mirror to measure the speed of light. The mirror was rotating at 1.87 times 10 to the 6 revolutions per hour. That's definitely worthy of a red circle there because it's not the standard units. We're used to hertz, which is revolutions per second. This is revolutions per hour, and of course we need to convert to hertz. The nose are 35 kilometers apart. Okay, that's good because that's the standard distance. Although we do want to circle kilometers there, just so we don't forget to convert that to meters. What did Michelson determine the speed of light to be? Well, let's get frequency in hertz first before we do anything else. If we've got 1.87 times 10 to the 6 revolutions per hour, then what do we got to do in order to convert that to revolutions per second or hertz? What's the conversion factor there, Rutger? Yeah, divided by 3,600. Now, that 3,600 comes from 60 times 60, right? We're dividing this 1.87 times 10 to the 6 by 60 to get revolutions per minute. Then we're dividing it by 60 again to get revolutions per second. Now, some of you might think, I get confused. Do I multiply or divide? I know it's 60 and 60, but do I multiply or divide? If you multiply, you're going to get a giant number. Okay, you got a big number here already. If you multiply it by 60 and then by 60 again, you're going to get an even bigger number. If you get an even bigger number, it doesn't make sense. You can't get more revolutions in a second than you get in an hour. So it's got to be divide. What does that work out to be when we divide that by 3,600? Rucker, do you have that? 519.44 revolutions per second or hertz. Remember what we said yesterday? Typically, we're dealing with a 10 to the 2 hertz in these problems. Not always, but typically. So we divide that by 3,600. We get 519. Odds are we've done the right thing now. All right. Next thing, we always do this. V equals d over t. And we always do this. T is equal to 1 over f. This t represents the time for 1/8 of a rotation. This t represents the time for one complete rotation. Remember, we're going to solve for a t. It's either little t or big T. I don't know which one it's going to be yet, but it's going to be one of the two. All I know is that it's going to be one of those 2 times, and it's not going to be the one that I want. So I'm going to have to use the one that I get to find the other one. Let's plug some numbers in here. We're trying to measure the speed of light, so we don't know what v is. We do know what d is. It's 70,000 meters, not 35,000 meters, not 70 kilometers, but 70,000 meters. We don't know what little t is. All right, no big deal. 1 over the frequency, 1 over 519.44 hertz, ends up giving me what? So do you have that one too? 1925 seconds. Now that's the time for one complete rotation. How do we find the time for 1/8 of a rotation now? Because of course the other time is the one we really want, right? Georgia, how do we get this to t, little t there? Okay, we're going to use v equals d over t, but we got to get little t first. We got big T, we got to change it to little t. Yep, divide by 8. Okay, that gives us little t, the time for 1/8 of a rotation. And what do we get when we do that? I'm going to guess 10 to the minus 4 seconds. I just don't know what the base is. .406 times 10 to the minus 4 seconds. Why did I guess 10 to the minus 4 seconds? It wasn't because I can do that in my head really, really quickly. I guessed 10 to the minus 4 seconds because that's what it is. When we're dealing with normal numbers for the Michelson experiment, that T18 is going to be 10 to the minus 4 seconds. Now, let's take that, plug it back into here. 2.406 times 10 to the minus 4 seconds. And what do we end up getting for the speed there? Whatever it was that I gave you in the answer sheet a minute ago. 2.91 times 10 to the 8. Hey, listen, if you get a number that's that close to the accepted value for the speed of light, odds are you're right. You could have made a mistake. If you did, it was a small one. Okay, it wasn't something like forgetting to convert kilometers to meters. It wasn't something like converting revolutions per hour to revolutions per second wrong. You did all that stuff right. The only thing that you could have done wrong if you get a number that's that close to 3 times 10 to the 8 is, maybe instead of dividing by 8, you divided by 9. or something silly like that, right? Okay, that's not likely to happen in one of these questions. So if you get a number that's close to 3 times 10 to the 8, you're probably, almost certainly, right. Okay, you guys feel comfortable with that? Okay, we'll have a quiz tomorrow just on this. Okay, we'll give you one question just on this. The reason I want to have a quiz right away on this and just this is because there is a very good chance you will see one of these questions on your diploma exam. Since the curriculum changed 6 or 7 years ago, it's been on almost every one of those exams. And the good news is they're all the recipe, right? None of them have been tricks. They're all very, very straightforward. If you can do it, you can do it, and you can get that 2% on your exam. So we'll have ourselves a little quiz tomorrow and make sure we're set for that as of tomorrow. The second worksheet that you had for homework was worksheet number 25. I mean worksheet number 15. All right, worksheet number 15, we need to go over number 5. Let's take a look at that now. It says a radio wave with a frequency of 3 times 10 to the 8 hertz. We know it's a radio wave, even if we weren't told that, right? Because microwaves are 10 to the 9 to 10 to the 12. So it's got to be a radio wave. Travels from ground level a distance of 50 meters, reflects off a metal roof of a building at an angle of 30 degrees, then returns to ground level. How long does this take, and what's the wavelength of the radio wave? Here's the ground. Here's the roof. This radio wave goes up like this, reflects off at an angle of 30 degrees. Now, it's not very clear here, to be honest, whether they mean 30 degrees as measured from the normal and 30 degrees as measured from the roof, right? That's not very clear. What we meant in this question was 30 degrees is measured from the normal line, because that's always the way we measure reflection, right? We talked about the law of reflection yesterday. So always measure from the normal line. We're told here that the distance that it travels from the ground to the roof is 50 meters. And then, of course, it's going to reflects off at the same angle. It's going to travel 50 meters back to the floor as well. So the total distance it travels is 100 meters. We know the frequency is 3 times 10 to the 8. And we know the speed is 3 times 10 to the 8. We're looking for the time, and we're looking for the wavelength. So to find the time, we're going to say V is equal to D over T. T is equal to D over V. That's going to be 100 meters divided by 3 times 10 to the 8 meters per second. That's going to be 3.33 times 10 to the 1 times 10 to the 2, 10 to the negative 7. 3.33 times 10 to the minus 7 seconds for our time. And our wavelength is going to be, this one's going to end up being easy. V is equal to F times lambda. Lambda is equal to V over F. 3 times 10 to the 8 divided by 3 times 10 to the 8 is 1.00 meters. Now, the way that I meant to write this question was to say that this distance was 50 meters, and then you would have had to find the distance that it traveled from the angle, but that's not what the question says. That's what it meant, but you're reading the question, and you can't read my mind and figure out what exactly I meant by it. Okay, this would have been a harder question. Okay, if this had been 50 meters, okay, this distance right here had been 50 meters, then you would have had to use that 50 meters along with the angle, okay, and found the hypotenuse. So it would have been cosine 30 degrees is equal to 50 over hypotenuse, and then you would have doubled the hypotenuse because there's 2 of them, and then you would use that as the distance. Does that make sense? So if I had have written it properly, okay, and if you had have interpreted that the way that I meant for it to be, then that's the way we would have done that question. How many people interpreted it that way anyways? Okay. Now, fair enough, because you're reading my mind, Braden. But in the end, if you did interpret it that way, okay, that's fair enough too, because that's not what it actually said, even though that's what I meant for it to be. Good? Let's keep moving with our whole law of reflection thing that we started yesterday. I'm going to draw this again here real quickly, but we did this yesterday, so you're not going to have to repeat. You're not going to have to draw it yourself again. We got an object in front of a plain flat mirror here, and we've got millions of rays of light reflecting off of that object. Those rays of light may be coming from the sun, maybe coming from a light bulb overhead. It doesn't matter where they're coming from. Okay, maybe it's just somebody glowing for whatever reason. They've drank radioactive something and they're glowing. I don't know. They're emitting light. They're reflecting light. Their light is coming from that person to the plain flat mirror. Now, there's millions of rays of light that are doing that, but we're going to pick 4 of them. We're going to pick the ray of light that reflects off of the guy's head. When it reflects off of the guy's head, maybe it goes straight toward the mirror. When it hits the mirror at 0 degrees, because we always measure it from the normal line, right? Hits it at 0 degrees, it's going to reflect back at 0 degrees. Angle of incidence equals angle of reflection. Hits at 0, reflects back at 0. Another ray of light reflects off of the guy's head, comes down like this. Well, it's going to reflect up here or down here somewhere, such that the angle of incidence right here equals the angle of reflection. If we extend that reflected ray back, and we extend this reflected ray back, then the guy's head should appear in the mirror over here somewhere where the 2 dotted lines intersect. Now, if this ray, we'll say ray number 1, intersected with ray number 2 over here on the left-hand side as solid lines, then the image of the guy's head would appear in front of the mirror. You guys know when you look at a 3D movie and somebody appears in front of the screen, it's a different technology. It's not exactly what we're doing right here, but that's the idea here. Okay? The idea is that we're not seeing the guy in front of the screen, in front of the mirror, we're seeing him behind the mirror. Okay? If these 2 rays, 1 and 2, as solid lines intersected, then they would be intersecting over here, okay, and you would see an image of the guy's head in front of the mirror, as if you do in a 3D movie. Okay? Now, that's not enough to show exactly the characteristics of the image yet, so let's draw a couple more rays. Let's draw a ray now that is reflecting off of the feet of this guy. Straight on. Bounces straight back. Ray number 3 looks like this. Ray number 4, it can go anywhere. We'll draw it right there. It's going to reflect something like this. Ray number 3 and ray number 4 don't intersect. So we're not going to get an image of the guy's feet in front of the mirror. Let's extend them, the reflected portion of those rays. So if we extend ray number 4 backwards like this, and we extend ray number 3 backwards like this, then we find the guy's feet, or the image of the guy's feet, appears over here, again, on the other side of the mirror. If we join the guy's head to the guy's feet, then we see the guy. Okay, we see the entire guy behind the mirror. When you look in the mirror in the morning, okay, all of you did this morning, you looked in the mirror, you saw yourself in the mirror. You appeared behind the mirror, and you appeared, let's talk about the characteristics, sometimes we call them the attributes. You appeared same size. Sometimes when you look in a mirror, depending upon the type of mirror, you may appear larger than you really are. You may appear smaller than you really are. But in this case, when you look at a plain flat mirror, you appear the same size as you really are. Sometimes when you look in a mirror, you appear right side up. Sometimes you appear upside down. Look in a mirror, hey, you're upside down. Depends on the mirror. In this case, we appear right side up, or we're going to say upright. And thirdly, this is the tough one. We talked about this a little bit yesterday. Real or virtual. A real image is an image that can be projected onto a screen. A screen. By a screen, I mean literally a whiteboard. I mean a smart board. I mean a movie screen. Okay, you can project the image. You can put the image from the mirror onto a screen. Okay, that's what we're doing right now with the lens and the projector overhead. We're projecting the image of whatever's on my computer onto a screen. We do that at a movie theater all the time. We don't do that when we look in the mirror in the bathroom in the morning. We're not projecting that onto a screen. You see the image by looking into the mirror. You don't look behind you at the wall and say, hey, there I am. There I am on the wall. Okay, it doesn't happen. You can't project the image of you from the bathroom mirror onto the wall, onto a screen. Okay? That's a virtual image. Now, how do we know that other than experience? And in the case of walking into the bathroom in the morning, intuitively you know you're not going to see an image of yourself on the wall. So intuitively you know that's going to be a virtual image. But how do we know if we come across a novel situation, one that we're not quite as familiar with? How do we know whether we can project it onto a screen or not? Here's the deal. If solid lines intersect, if lines 1 and 2 intersected as solid lines, and lines 3 and 4 intersected as solid lines, then that would be a real image. We could project that onto a screen, but they don't. 1 and 2 don't intersect, 3 and 4 don't intersect. We have to extend them. We have to make them dotted lines. When we extend them as dotted lines, they do intersect. That makes it virtual. That's how we know that we could not project this onto a screen. So remember that. You're going to see situations later today where solid lines intersect. That's a real image. We don't have to project it onto a screen, but we could. Okay, we're going to see situations later on today as well where we have dotted lines intersecting. That's a virtual image. We can't project that onto a screen. In order to see that one, we got to stand right here, okay, where this guy's standing in this diagram, physically look into the mirror, and when you do that, you're going to see the image. You're just not going to see the image on the screen, that's all. Yep. Yeah, no, that's a good point, Rucker. Rucker's talking about, they call them short throw projectors. Some of the smart boards in the school, I mean, mine's, what is that, like 15 feet away? 12, 15 feet away from the screen here. Some of them are literally like 2 feet away from the screen. And they use a little bit of a different technology than these ones do because they can't magnify it enough in that short distance, right? You'd have to have a ridiculous lens in order to magnify it enough when it's 2 feet away from the screen to have it the size of this. So what they use is a mirror. They use a lens to project it onto a mirror, and then they use a mirror to project it onto the screen. Now, Rucker, you see that on a screen, right? So you said it makes you wonder about that. It's not a plain flat mirror. In that case, it is a real image. Okay, if we do a ray diagram to describe that, okay, it's a real image. Okay, but in the end, as I said, Rucker, that's not a plain flat mirror. Okay, does that make sense? Oh yeah, you know what? Actually, yeah, that's right. You got a good point there, actually. Yep. Yeah, I'd have to think about that, actually, Rucker. It's a good point, but I got to think about that one. Yeah, you got me stumped here for a second, actually. We finished off yesterday talking about two different kinds of mirrors, curved mirrors, concave and convex, converging or diverging. A concave mirror is a mirror that's caved in the middle. It's thinner in the middle than it is at the edges. It's called a converging mirror because rays of light, at least some of the rays of light in a converging mirror or a concave mirror will converge, they'll come together. Whereas a diverging mirror, the rays of light will diverge or they'll spread apart. Now, depending upon where you're standing, the characteristics of the image that you're going to get are going to look a little bit different. Okay, in this case, hey, the guy is standing really, really close to this concave or converging mirror. That's going to produce an image that you can see here quite clearly is bigger. Hey, the guy's face is massive in this. Okay, instead of being same size like it was in the last ray diagram we drew, the characteristic would be that it's bigger. It is upright because you can see his face is still right side up. And in this case, it would be probably virtual. Okay, in the end, we can see a real image by looking into the mirror. We just can't project a virtual image onto a screen. This is probably virtual, although we'd have to draw the ray diagram to actually determine whether we could project it onto a screen or not. The bottom one, diverging, convex. This one's the one that's rounded, thicker in the middle than it is at the edge. This is the one that we see at the hot tub at the pool in Okotoks, right? We see that so the lifeguards can kind of go around the corner. They can see the entire hot tub without kind of leaning over and bending around and whatever. They can see, you can cover more area with a diverging mirror or a convex mirror. The downside is that although it's a virtual image and we can look into this mirror in order to see it, see everything, Okay. Although everything is upright, which is good, everything is also smaller. That's why it allows us to see more, because it's smaller, right? If it was same size or bigger, then we wouldn't be able to see much of the hot tub in that mirror. Okay? You'd see one guy's head, which wouldn't be very productive, right? So two kinds of mirrors: converging, which allows rays of light to converge, at least some rays of light to converge, and diverging, which allows rays of light to diverge. Today what we're going to do is draw ray diagrams for all the different possible positions of objects for both of these rays, for both of these mirrors. And we're going to put an object in position 1, position 2, position 3, position 4, position 5, 5 different possibilities for both of these, and see what the different characteristics look like. Unlike a plain flat mirror, where the characteristics will stay the same no matter where you put the object, in these ones, the characteristics are going to change depending upon where the object is. What kind of mirror is this? Sorry? It's concave. What's the other name for a concave mirror? Converging. Remember I said that some rays of light will converge? Some rays of light will converge at a point where we call the focal point. This point right here that's kind of to the left of this converging mirror. Now, which rays of light will converge there? I said some will converge there. All rays of light that are parallel to the principal axis. Now, what's the principal axis? The principal axis is an imaginary line that's drawn at 90 degrees to the mirror, straight through. This is the principal axis. If rays of light are parallel to the principal axis, don't draw this yet. If they're parallel to the principal axis, they will always reflect down through or up through the focal point. See that? We call it converging because all rays of light parallel to the principal axis will converge at the focal point. How many people have satellite TV versus cable? Got a little satellite dish on the side of your house? You don't really have a satellite on the side of your house, right? The satellite is orbiting around the Earth at however many thousands of kilometers. The satellite dish on the side of your house is a receiver. And it looks something like this, doesn't it? You got a shape that looks something like this, and then you got this arm that sticks out, and then you got this thing at the end of this arm like this. That thing at the end of the arm is the focal point of that. Well, it's not a mirror, but it's a reflector. It reflects radio waves that are parallel to the principal axis. And because they're coming from such a far distance, most of the rays that strike it are pretty much parallel. It reflects them through the focal point, and that's where the actual detector is at the focal point. So they all go through like this. They all kind of get magnified right there at the focal point, get sent to the box inside your house, and then get sent to your TV from there. All rays parallel to the principal axis converge at the focal point. Now, we got another point that we want to label here as well. We call it the center of curvature. The center of curvature is if we drew a complete circle here, then the center of curvature would be literally the distance from the center of the circle to the mirror. Now, what's interesting about this is that the focal point is exactly 1/2 of the center of curvature, always. So if the focal point is 5 centimeters, then the center of curvature is 10 centimeters. If the focal point is 20, then the center of curvature is 20. Another name that we could give the center of curvature would be the radius. The radius of the circle, the radius of the mirror, the center of curvature, which is twice the focal length. Now we got an object, in this case, that's beyond the center of curvature, an object that is far enough out that it's on the other side of the center of this circular mirror here. What's the image going to look like as a result of this object and this mirror, as opposed to the plain flat mirror that we looked at in the last case? Well, there's 3 rays that we can draw here, but the good news is we only ever have to draw 2 of them. There's 3 options, we draw 2 of them. Let's pick the first option first, because it's the easiest one. The first option is that ray of light that comes from the top of the object, that reflects off of the top of the object straight towards the mirror. Same as it was for the plain flat mirror that we drew a few minutes ago. Reflects off of the guy's bald head towards the mirror See what happens to it. Well, in the other mirror, it reflected straight back. It doesn't here. It doesn't reflect straight back here because the angle of that mirror is different. It needs to reflect such that the angle of incidence equals the angle of reflection, which is going to make it reflect down here through the focal point. It's a ray that's parallel to the principal axis, right? It's got to reflect through the focal point. Now, that's only one ray. That's not enough to give me any characteristics of this image yet, or any attributes of this image. We don't know whether it's right side up, upside down, larger, smaller, same size, real, virtual. We don't know yet. We have to draw another ray. We have to get rays of light intersecting to determine what kind of image it is. Doesn't matter whether they're solid or dotted lines intersecting, but we got to get rays of some type intersecting. Let's draw our second option here now. Okay, we just drew our first. The second object is, once again, from the top of the object. Remember, there's millions of rays here. We could draw one like this, anywhere we want. But we're going to pick the one that goes from the top of the object down through the focal point. How do we know there's a ray of light that goes down through the focal point? Because there's millions of rays of light. There's got to be a ray of light that goes through the focal point. There's a ray of light that goes everywhere. We're just picking this one because we know what happens to this one. It's easy to predict. Goes to the focal point. What do you think it's going to reflect without looking at the notes that we have below there? John? Good. If the one parallel went through the focal point, remember we've talked about this a few times, the symmetry of physics, right? If the one parallel goes through the focal point, then the one that's through the focal point is probably going to go parallel to the principal axis. Now, that's enough right there. We don't need to draw the third ray, actually, for this particular diagram. That's enough to tell us where the image is formed. The bottom of the image is going to be formed at the principal axis, just like the bottom of the object was formed at the principal axis. The top of the image is formed where the rays that came from the top of the object converge, which is right here. So in other words, the image formed is going to look like this. From the principal axis down to where the rays converge. Remember we talked about three characteristics, three attributes. The first one related to the size. Is this image, okay, the red image, the red one is the image, the black one is the object. Is the image larger, or is it smaller, or is it same size as the object? I think it's pretty clearly smaller here, right? This red line is shorter than the black line. We're going to say the image is smaller. You look into the front side of a spoon. When you're far away from the front side of that spoon, you're going to see yourself smaller and upside down. Try it. Hey, try it. Take a big enough spoon where you had and a shiny enough spoon where you can actually see something. Hold it far away from yourself. You will see yourself in that mirror, in that spoon. You will be smaller and you will be upside down. You just got to make sure you're holding it further away than the radius of the spoon, right? Because if you're holding it really close to it, then the image characteristics will be different, right? Second characteristic, smaller. We said it's smaller. It's going to be right side up or upside down. Ready? Upside down. We're going to say it's inverted. I don't really care what word you use there. Okay, if you said it was upside down, that would be fine. Flipped over, that would be fine. Okay, on our diploma exam, we're not necessarily going to see the word inverted. We're just going to have to know that it's upside down. And whatever word they use to describe that is the word that we pick, right? Finally, the third one. This is the tough one. Always the one that gives people trouble in the beginning. Is it real or virtual? Is it real or is it virtual? Cole, you look like you're ready to answer that question for me. Real or virtual? How do you know it's virtual? Could it be projected onto the screen? Just because it's virtual doesn't mean, just because it's real doesn't mean that it is being projected onto something. It just means that it could be projected onto something. We could have a real image and have no screen around for a million miles. Brad, are you going to say virtual as well? Or real? Who says virtual? Hands up if you think virtual. Hands up if you think real. Oh, look at this. Why real? Why real, Dave? Solid lines are intersecting. Yeah, look, it's not dotted lines, it's solid lines intersecting. That means we're not necessarily projecting that onto a screen, Cole, but we could if we wanted to project it onto a screen. Hey, where would we need to put the screen in order to have a focused image? Where would we need to put the screen? How about right here? Right? You have to put the screen right there in order to see a focused image. If you put the screen, how about if you put the screen right here, what would happen? Would you see an image? Would you see the picture on the screen? You would, but it wouldn't be focused, right? It would be kind of blurry. That's the problem that I have with my eyes. It's not a mirror, it's a lens, but similar principles apply. Okay, when I take off my glasses, the rays of light that are coming through the lens of my eye are converging. They're supposed to converge at the retina of my eye, but guess what? They're not. So what's happening to them? They're converging in front of the retina. Now, I can still see an image on the retina of my eye. It's just not a focused image because those rays of light have converged together just in front of my retina. They're still shining onto my retina. They're just not converging at my retina. So I'm going to see something. Now, the further in front of my retina that they converge, the worse the blur is, right? The worse I see, and the stronger the glasses I need to correct that. All right. I told you don't need to draw the third ray for this diagram. You only ever need to draw two, but let's draw the third one anyways, just to illustrate that you could pick the third one instead of the second one, or even instead of the first one for that matter. The third ray goes from the top of the object, down through the center of curvature, down through the center of it. Hits the mirror, and it's going to reflect back upon itself. Where does that third one intersect? Exactly the same, right? So if I picked ray 1 and ray 2 and ray 3, or ray 1 and ray 3, they all intersect at the same place. So I'm going to get, in all three cases, the same three characteristics. It's going to be my image form right there. Okay, I drew that third ray not to say that you should draw the third ray. If you draw the first two rays and you get them intersecting, stop. Don't bother with the third one. Okay, I just wanted to show you what the third ray looks like for the event, in the event that we need to draw it. And we will need to draw it for some of these ray diagrams, just not for this one. Let's draw another possibility here. Okay, you've got your template with 5 different possibilities. The first one is where the object is well beyond the center of curvature, well beyond this one. So the object was out here. Let's draw the next one where the object is at the center of curvature. So the object is right here. Now, there's 3 rays that I can draw. The good news is I'm only going to need to draw 2 of them. And in this case, it's going to end up being the first 2. We won't even bother drawing the third one here. First ray, from the top of the object parallel to the principal axis. Where does it go? Down through the focal point. Second ray, from the top of the object down through the focal point. Where does it go? Parallel to the principal axis. Now, sometimes you got to fudge this a little bit because my template isn't perfect in terms of the curvature of the mirror. If it was perfect, you wouldn't have to fudge it. This should appear directly below the center of curvature. And it should have the following characteristics. It should be the same size. The red arrow, the image, should be the same size as the blue arrow, which was our object, the guy that's actually standing there. It should clearly be inverted. And Cole, real or virtual?
Real.
Real? How do you know?
Solid line.
Good. Solid lines intersect. Doesn't mean that we do have a screen there. It doesn't mean that it is being projected onto a screen. But if we did put one there, we could project the image onto a screen and just look at the piece of paper, look at the screen, whatever it was, and view the image. Let's try the next possibility. The next possibility is when we have our object getting closer and closer to the mirror, right? This time it's in between the focal point and the radius or the center of curvature. In other words, It's about 3/4, well, it's somewhere in between half the way and all the way to the center. So maybe about 3/4 of the way towards the center, maybe 2/3 of the way towards the center. First ray that we're going to draw is on the top of the object. It's the mirror, goes down through the focal point. Second ray goes on the top of the object down to the mirror. Now, my mirror kind of disappears there. We're going to pretend the mirror's still there. Reflects off of the mirror back parallel to the principal axis. Remember, parallel through the focal point, parallel. Image is going to be formed right here from the principal axis again to where the lines intersect again. What are the three characteristics of this one? Tyler, what's the first one? Bigger, smaller, same size? It's bigger. The red line is clearly bigger than the blue line here. The image is clearly larger, bigger, whatever you want to say, than the object is. Once again, on an exam, do they use the term larger? Do they use the term bigger? Do they use the term enlarged? I don't know. Doesn't really matter. They all mean the same thing, right? Maddie, question? Yeah, you know what? That depends. It depends upon where this object, that's a good question. Maddie's question was, is it supposed to be behind the center? Exact position is not critical here because that varies depending upon where the object is. Okay? In some cases, it's going to be closer to the object. In some cases, it's going to be further away from the object. Bottom line is the characteristics will be the same no matter where this object is, as long as it's between F and C. Its placement will be different. So as long as you're getting the right characteristics, don't panic about its position. The only reason that we were kind of sticklers on the position of this one is because it's supposed to appear directly below the object, right at the center of curvature. Okay, first characteristic, it's larger. Next one, right side up, upside down. It's upside down, it's inverted, good. Or if you want to write upside down, if that makes you feel better, go ahead. As long as you know what that means. Real or virtual? Right? It's real. Solid lines intersect, right? We haven't seen one of these mirrors yet where it's virtual, where dotted lines intersect. We saw it in our plain flat mirror. It was always virtual. But these ones have always been real, at least so far. Now remember, you want to project this onto a screen, you put a screen right there where the image is formed. Do you need to project it onto a screen? No. You can look into the mirror to see this. You can look at the spoon and see yourself on the spoon. You just don't need to look at the spoon. You could put a piece of paper in the right place and see the image of your face on that piece of paper. Next one. This time our object is exactly at the focal point. Our first ray is going to be from the top of the object, parallel to the principal axis, down through the focal point. Our second ray this time is not going to be from the top of the object through the focal point. Our second ray is going to be from the top of the object through the center of curvature. But we're actually on the right side of the center of curvature, so it's going to be going away from the center of curvature. You see this, guys? If I extended this back, if I extended this one back, it would go right through the center of curvature. So that second ray is going from the top of the object as if it's coming from the center of curvature, as if it's coming from the radius. What you need to do there is take a ruler, basically, or a straight edge, and just line it up with the center and the top of the object. And then just draw your line from the top of the object to the mirror. Where's that going to go? Where's it going to reflect? Well, it reflects back upon itself, right back through the radius or the center of curvature. Do those solid lines intersect? They do not. So what do we got to do? Let's extend them. Let's extend them back here. Here's the reflected ray, the first one extended back. Here's the reflected ray, the second one extended back. Do they intersect? What do you know about this image? there is no image. There are no characteristics when there is no image. So picture this now. You got a spoon in front of you. You got the spoon really far away. You see yourself in that spoon. And what do you see yourself as first? You see yourself upside down in that spoon and really, really small. You bring the spoon closer to you. As you bring the spoon closer, you still see yourself upside down, but now you're getting bigger. As you bring it closer, you see yourself in the spoon, but even bigger. In fact, now the image of you in the spoon is bigger than you are. So you have to, if you want to see your entire body, you better have a big spoon. Otherwise, you're only going to see a small portion of you. You're now still upside down, but you're now bigger than you really are. Or at least the image of you is bigger than you really are. You bring the spoon even closer to the point where you're at the focal point. You disappear completely. There is no image of you in the spoon. Look at the spoon. You don't see yourself. Hold it a little further back. Oh, I see myself bigger and upside down. Bring it closer again to the point where the spoon is at the focal point. Don't see myself. Disappeared. See nothing there. That's a good way, by the way, to determine what the focal point of the spoon is. Where do I disappear? Okay, wherever I disappear, that's the focal point of the spoon. If you double that distance, that's going to be the radius of curvature of the spoon. One more. This time I'm going to put my object really, really close. Really, really close to the spoon or to the mirror. My first ray, same as my first ray always is, parallel to the principal axis, down through the focal point. Second ray, well, I'm actually not going to draw that second ray again. I'm going to draw the third ray, which is from the top of the object away from the center of curvature. Same as it did last time, it reflects back upon itself, down through the center of curvature. Do those two rays intersect, John? No, they don't. So what do I got to do? Yeah, draw fake lines or dotted lines back. Okay. Now, you look in a textbook, they might not do dotted lines per se, but they're going to extend these rays back. Okay. I just like to call them dotted lines because it's a nice, easy way to distinguish between the actual rays and, as John called them, the fake rays. Let's extend this one back, straight back. Let's extend this one straight back, and oh, look, those ones intersect. They intersect right there. What do you know about this one? Well, there is an image formed. What are the characteristics or the attributes of this one? It is larger, smaller, same size. Braden? Look at the red line, look at the blue line. The red line is larger, right? Or bigger, or enlarged, or whatever you want to call it. Is it right side up or upside down, Sean? Yeah, it's upright or right side up. And is it real or virtual? What is it? This one's virtual. How do you know? Good. Dotted lines cross. This one's virtual. Isn't that this diagram right here? Or this picture right here? Guy's looking into the mirror. He sees himself bigger, right side up. He's looking into the mirror. Look at it. He's really close to this mirror. He's inside the focal point, right? Between the mirror and the focal point of this mirror. That's exactly what this one is. So if this guy stands right there, this is what he's going to see. As he backs up, what's going to happen? Oh, at some point, he's going to disappear. He's going to be looking into that mirror and see nothing. And then he's going to back up a little bit further, and all of a sudden he's going to reappear, but now he's going to appear still bigger, but this time upside down. And then as he backs up even further, he's going to appear smaller and smaller and smaller and smaller to the point when, backs up far enough and he's going to appear so small that he probably can't even see himself. So it's not like a plain flat mirror where the characteristics are the same no matter whether you stand really close to the mirror or far back from the mirror. In this case, it depends a lot on where you stand or where the object is relative to the mirror. Get it? Hey, that's why in a fun house, in the fun house mirrors. How many people have ever like been in a fun house or something like that where they've seen those curved mirrors, right? Sometimes they're curved outwards, sometimes they're curved inwards. Okay, that's why, hey, depending upon where you're standing, okay, you see something different than your friend, right? You're standing really close and you see yourself big and right side up. You're standing far back and you see yourself small and upside down, or big and upside down, or whatever, depending upon where you're standing. And then your friend over there says, I don't even see myself at all. How come I'm not in the mirror? Well, because he's standing at the focal point of the mirror. That's why he can't see himself. Okay, let's take a look at this mirror. Good news is these ones are actually quicker and easier because the ray diagrams are all the same. This is a convex mirror, also known as a diverging mirror. We're going to assume our object is on this side of the mirror, on the convex side of the mirror. Now, why do we have labeled over here, on the other side, two parts, two spots? We're going to call this F, we're going to call this C. But remember, it's like now you're on the outside of the soccer ball as opposed to the inside of the soccer ball. You're looking at the bulged out part as opposed to the caved in part. The center of this circle is going to appear, okay, if this is a soccer ball, okay, that's not really the center, but you know what I mean though. The center of the circle is going to appear inside or on the other side of the mirror. So is the focal point. There are three rays that we can draw here as well, but I'm only going to tell you about two. When we had concave or converging, we needed to know all three rays because in the first three ray diagrams, we drew 1 and 2. In the last two ray diagrams, we drew ray 1 and 3. This time, we're always going to draw 1 and 2. First ray, parallel to the principal axis from the top of the object. Now, remember, converging, all rays parallel to the principal axis converged at the focal point. What's going to happen to these guys, the ones that are parallel to the principal axis? They're going to diverge away from the focal point. So I'm going to draw this upwards like this. Now, should use a ruler here or a straight edge to make sure that this point right here lines up with this point right here. You don't want this just going off in any kind of random direction. It should go off in a very specific direction away from the focal point. It's all governed by the law of reflection, right? The angle of incidence equals the angle of reflection. We just don't need to measure the angles because we know where the focal point is. We know what's going to happen there. Okay, although if you looked at this closely, okay, here's the surface at this point. At that point, there's the normal line. And would you look at that? The angle of incidence equals the angle of reflection. Okay, second ray. Second ray is going to go from the top of the object, from the top of this guy's bald head, down towards the focal point right here. Except it can't actually make it to the focal point. How come? Why can't it make it to the focal point? There's a mirror in the way. So what's it do? Well, it goes toward the focal point. It hits the mirror. It's going to reflect off of the mirror. Where's it going to reflect? Not straight back, no. Now, that third ray, Rucker, that we don't have to draw for any of these, would go from the top of the object down towards the center. It would reflect back. Okay, we're not going to draw that one, though. We're going to draw the one that's from the top of the object down toward the focal point. Okay, it's going to reflect. Okay, it's going to reflect parallel to the principal axis. Do those two rays intersect with each other? Good. The dotted lines do. Good. The solid lines that we have here aren't intersecting with each other, so let's extend them back. Here we got the first one, the first reflection going back to the focal point. The second reflection is going back parallel to the principal axis. And the image that we see here is, look at that. It is clearly smaller, way smaller in this case. Way smaller than the object. Is it right side up or upside down? Dallas, upright or inverted? Upright. And Caitlin told me before I even drew the dotted lines that it's dotted lines that intersect, which means what kind of image is it, real or virtual? Virtual image, good. In order to see this, we need to look into the mirror. Let's go back for a second to that first page on these curved mirrors. Take a look at the diverging one. What do you see there? You see a guy standing in this mirror. It is smaller, that is right side up, and that is virtual. Now, the nice thing about these diverging mirrors is that although if you stand in a different place, if the object is somewhere different, the image will be in a different spot and it'll be a different size, but the characteristics will still be the same. You're going to find when you draw the next 4 ray diagrams, and you're going to do that yourselves at your desk right now, that the characteristics are the same. In all 5 cases, it will be smaller, it will be upright, and it will be virtual. Now, it may be bigger than the first diagram, but it won't be bigger than the object. It may be smaller than the first diagram, but the characteristics of the image will still be the same. Proportions different, but characteristics or attributes still the same. Right? Okay, there's the value in that convex or that diverging mirror. Right? You put that diverging mirror in the corner, the top corner of the convenience store, and it doesn't matter where the guy who's trying to shoplift is standing. You can see him in the mirror. He may be smaller if he's further away from the mirror, but you're still going to see him in there because the characteristics are still going to be the same. He's not going to, depending upon where he's standing, appear upside down in the mirror. Okay, give you a chance to draw those ray diagrams now. So where have you seen convex mirrors before? Clearly you've seen them if you've gone swimming at the rec center. You've seen them probably maybe in an old corner store. You don't see them at 7-Eleven anymore because everybody's got video cameras, but some corner store in a small, back alley section of Calgary or something, maybe you've seen one of these where the store clerk hasn't installed video cameras. He wants to be able to see the entire store. Where else have you seen them? There's actually one. Have you ever driven across the high-level bridge in Edmonton? How many people know what I'm talking about? The big bridge that looks like a train bridge almost. Really, really narrow bridge. There's a big concrete abutment here. Here's the bridge going across this river, really, really high. And there's an entrance to the bridge coming from this side. There's an entrance coming from this side. There's cars coming this way, and there's cars coming this way. Now, it's 2 lanes, but they're very, very close together. It's a very, very narrow road. Okay, so it's kind of freaky, actually, when you're coming around this corner right here, and there's people coming around this corner, and it's almost like you're fighting for the same lane, but you can't see them coming. Okay, they've got this big convex lens up here and this big convex lens up here. Why? So that when you're coming around here, you can see everybody coming around here. You know if somebody's coming or not. So you know if you have to yield or not. Same deal on this side. Where else have you seen them? Oh, you're going to love this. Girls are going to love this. Okay. Guys too, possibly, but it happens more for girls than it happens for guys. You know that we can have convex not on 2 planes, like if you cut off the side of a soccer ball, it's convex on the x-axis and the y-axis, right? You can have it convex on just the x-axis or on just the y-axis. Well, what that does is changes the proportions on one way. So if you have it like this, horizontally, then that makes everything on the horizontal axis smaller, but everything on the vertical axis, it's a plain flat mirror vertically, right? So you're just normal. So you appear the same height, but yet narrower, slimmer. So wouldn't it be convenient for, at high-end department stores trying to sell you this dress to make you look really good in that dress, to make you look 4 or 5 pounds lighter in this dress? I'm not suggesting that every store does that, okay? But be wary, because some stores do. It's so subtle, they don't want to make it so that it's like, oh my goodness, like I just lost 30 pounds. Like you can't make it like that, because people are going to know, right? But if you make it subtle, then people might not notice. They just think they look good. Now, I don't know that they necessarily do that in guys' change rooms as much because, first of all, guys don't really go into change rooms. Guys buy it, and if it doesn't fit, then they return it later on. Second of all, guys just don't care as much. Guys don't care as much if they're skinny or what. Ladies, be wary. Okay, they're out to get you.